Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. In this module, we will learn how scheduling is handled in the Linux operating system. So, the learning objectives for this module are to learn how Linux schedules user processes, how real-time tasks are scheduled in the Linux OS, and how scheduling of kernel tasks are being done in the Linux operating system. So, what is scheduling? We have a processor or the CPU, and the processor's time or the CPU time has to be allocated to different tasks which are running within the operating system. So, the job of allocating the CPU's time to the different tasks which are competing to use the CPU is being done by the scheduler, and this job is called scheduling. And when you are looking at this Linux operating system, it supports a preemptive multitasking. That is, when you say that it is multitasking, many tasks can be active at a particular time, which means that many tasks can be waiting to use the CPU, or many tasks can be waiting to go to the running state and to execute. And it is also a preemptive kind of a system, which means that whenever a process is currently executing, it is possible to preempt that process or take away the CPU from that process and give the CPU to some other process, or the process by itself may not relinquish the CPU, but the process will be preempted from the CPU. So, Linux supports preemption as well as multitasking, and this process scheduler is the one which decides which process has to run next and when each process has to run. So, this is decided by the scheduler. So, based on many factors, the scheduler comes up with this decision. So, in this module, we will understand how this kind of decision is being made in the case of the Linux operating system. So, when you are looking at scheduling means it is not just running and interrupting of user defined processes in Linux, but scheduling also includes the running of kernel tasks. So, what do you mean by kernel tasks? Say the user process want to execute some kernel code as a part of the execution. Say for example, when it is a system call, when there is a system call, the user calls a system call, and as part of the system call or for the execution of the system call, a kernel code will have to be executed, and this will be done in kernel mode, and that running or the running of that kernel code will be a kernel task. So, tasks that are requested by a running user process and the tasks that are executed internally on behalf of the kernel are called kernel tasks. So, when there are a number of kernel tasks that are available, then the operating system should take care of scheduling those tasks as well. So, it is not just scheduling the user process, it is also scheduling the kernel tasks. Now, we will first see how Linux takes care of scheduling user defined processes. So, Linux uses two algorithms for process scheduling. One is for the regular non real time tasks and the other is for real time tasks. So, when you have non real time task, it uses or Linux uses a time sharing algorithm such that fairness is taken care of, or it uses a fair preemptive scheduling algorithm. And when you have real time tasks, rather than giving more importance for fairness, it gives more importance for priority. So, these are the two cases or the two ways in which Linux handles user defined processes. Now, we will see this time sharing fair algorithm. This algorithm, which is called the completely fair scheduler or CFS, was not available in Linux earlier to the version 2.6. So, this was introduced only in version 2.6 and it is used after that. So, what is this CFS algorithm or completely fair scheduler algorithm. This gives more importance for the fairness. So, this is a preemptive, it is a priority based algorithm and it has two different priority ranges. One is the priority that has been given for real time process and the next is the value that is being assigned based on the nice value of the process. So, if it is a real time process, then there needs to be some priority being assigned for that process and the range of the priority will go from 0 to 99. But a process can choose to be nice to other processes by choosing a nice value. So, this nice value we have seen in a different module earlier can be set by using the system called nice. There is a nice system called, there is a system called nice which can be used to set the nice value of a process. So, this nice value, if the nice value of the process is very high, then it means that the process is being nice to others or the process is getting itself a lower priority. So, if the nice value is small, then the process has got a higher priority compared to other processes. So, in the earlier algorithms, in the early day Unix, the variables that were given importance were the priority and the time slice. Fairness was not considered at all. But this algorithm, as I told you, the CFS algorithm implements a fair scheduling algorithm. So, all processes should be treated in a fair manner and hence all the processes are allocated a proportion of the processor's time. So, the CFS algorithm, it calculates how long a process should run or use a CPU based on the number of total processes that are available. Say if there are n number of runnable processes and all these n processes are waiting to use the CPU, then each process is allotted 1 by n of the processor's time. So, this allotment is again adjusted by weighting each process allotment by its nice value. So, if there are 10 processes, then generally 1 by 10th of the CPU time to be assigned should be assigned to each process. But if each of these 10 processes have different nice values, then different weights will be given for each of these processes because depending on the nice value they have. So, if the process have a default nice value, they are given a weight of 1. That is, the priority is unchanged. So, the default nice value is assigned for the process, they do not have a higher value or a low value, then it means that the weight for the process is 1. But if a process has got a smaller nice value, then it should be assigned a higher priority and hence it will receive a higher weight. If the process have a larger nice value, then they are nice to others and hence they need to lower the priority or they are having a lower priority and hence they will receive a lower weight. So, based on the nice value, a weight is assigned to each of the processes and now based on this weight, the time duration for which a process should run is decided by this CFS algorithm. So, the CFS will run each process for a time duration which is proportional to the weight of the process divided by the total weight of all the running processes. So, if the weight of the process is less, then it will get a less time duration. If the weight is high, it will get a higher time duration to use the CPU. Now, to calculate the actual length of time that a process should run, another variable is used which is called a target latency. So, this target latency is another thing that needs to be considered to assign the time duration for which a process will run. So, what is this target latency? The target latency is the time duration during which every runnable task should run at least once. So, you have a time frame kind of thing and within that time frame all the runnable process should get at least some amount of time or some amount of execution time. Assume that the target latency is 10 milliseconds, or the time frame or the total time frame is 10 milliseconds, and you have two runnable processes, and both the processes have the same priority and same wait, and both are waiting to use the CPU. And hence these two processes should run within this time frame of 10 milliseconds. Because they have got equal priority, both will get the same time duration to run. So, each of these processes having the same weight, and hence they should be given the same proportion of the process time. So, the 10 milliseconds is now divided into 2, and each of the processes will get 5 milliseconds to use the CPU. So, the first process will run for 5 milliseconds and the next process will run for 5 milliseconds, and both the processes complete their execution within this 10 milliseconds. Suppose if there are 10 runnable processes and you have 10 milliseconds as the time frame, how long will each process get? Each process will get a time duration of 1 millisecond. But if there are 1000 processes, each process can run only for 1 microsecond. Now, think of the cost involved in the context switching. See, within this 10 milliseconds time duration, there should be switching 1000 switches happening, because each process can get only 1 microsecond, because you need to be fair enough, you need to give each process some amount of execution time or some amount of CPU's time, and there will be 1000 switches that are happening, 1000 context switches that are happening. And we all know that this context switch is an overhead. What happens during a context switch? During a context switch, the state of the old process will be saved and the state of the new process have to be loaded, which means that this will take some amount of time, and hence this switching time becomes an overhead. So, if you are scheduling process for short lengths of time, it is found to be inefficient. So, what can be done? Another configuration variable is introduced called the minimum granularity. So, what is this minimum granularity? It is the minimum length of time any process is allotted the process time. That is, once a process is given the CPU, it will execute or it will use the CPU at least for this minimum amount of time, which is equal to the minimum granularity. So, regardless of the latency, the process will run for at least this amount of time. But what is the advantage here? Because of this, we reduce the number of context switches, but the problem is that all the runnable processes may not get their CPU time or may not get the CPU time within that single time frame, and hence fairness is violated. So, now that we have seen how non-real time processes are being scheduled, we will see how real time scheduling is done when there are real time processes involved or real time processes that are waiting to use the CPU. So, in the case of real time scheduling, Linux implements two real time scheduling classes. One is first come first served and the other is round robin. In both the cases, each process has a priority in addition to the type of scheduling that has been used, and always the process with the highest priority is run. So, if it FCF is, what is done is that the process with the highest priority is given the CPU, that process will complete its CPU burst time and then it will relinquish the CPU. So, after the highest priority gets a CPU, if another process with a more higher priority than this process comes, that process will not be given the CPU. This process will not relinquish. Once it gets the CPU, it will continue and it will use the CPU. But in the case of round robin, what is done is that a process will be given some amount of time, and then only for that duration of time they will use the CPU, and then they by themselves relinquish the CPU. Suppose if you have many processes which are waiting with the same priority, real time processes that are waiting with the same priority, then the one that was waiting for the longest amount of time will be scheduled or will be given the CPU. So, as I told you, FCFS processes they continue to run until they exit or they block, but round robin processes they will be given some amount of time and all the processes will go in a round robin and get the CPU, but the thing is that if a higher priority process arrives, round robin process can be preempted and they will be moved to the end of the scheduling queue. If you have round robin process of equal priority, they will automatically do time sharing. And here Linux takes care of only soft real time scheduling. It does not worry about this hard real time scheduling, it does soft real time scheduling in the sense that soft real time process will be given higher priority compared to the other process. If it is a hard real time scheduling kind of concept, then you need to have a different variant of Linux. There are devices which use different variants of Linux to implement hard real time scheduling, but generally Linux does only soft real time scheduling. Now, we come to the next part, that is how kernel tasks are scheduled. So, the way the kernel schedules its own operations is different from the way the user processes are scheduled. Whatever we had learned till now is how the user processes are scheduled, where we looked at the CFS algorithm and the real time task scheduling, but now we will see how kernel tasks are being scheduled. So, what do you mean by kernel task? Kernel tasks are tasks that are run in the kernel mode. When will a kernel mode be executed? The kernel mode execution will happen whenever user defined process is asking for an operating system service. Say the user defined process is calling a system call and hence a kernel code has to be executed, or say a page fault occurs and hence kernel code has to be executed, or say there is a device driver, there is a hardware interrupt and hence the routine or the interrupt service routine corresponding to this interrupt has to be executed. In all these cases, the kernel's code has to be executed. So, this kernel synchronization, it requires a framework that will allow the kernel tasks to run without violating the integrity of shared data. So, within the kernel code, there will be a lot of data structures, a lot of data that could be shared between different kernel tasks. So, in that case, how do you ensure the integrity of the data structures maintained within the kernel? That is, many tasks may try to access the kernel data structures simultaneously. How simultaneously? How is that possible? Suppose you have a task that is accessing the file table which is maintained within the kernel. So, there is a file table maintained in the kernel and one task is accessing this file table. In the meantime, say the interrupt occurs. So, when the interrupt occurs, the interrupt service routine has to be executed. So, this interrupt service routine, say if the interrupt has got a high priority and this first task which was accessing the file table is stopped in the meantime and the interrupt service routine is executed. And as a part of the interrupt service routine, if the interrupt service routine wants to access this file table that was being used by another task, that should not be allowed, or this interrupt service routine should not be allowed to access the file table. If it is allowed to access the file table, then it may result in data corruption. So, how do we ensure this? How is this taken care of? Till the version 2.6, the kernel was non-preemptive. Linux kernel was non-preemptive. That is, a process which is running in the kernel mode cannot be preempted even if a process with high priority is waiting. So, if a process is executing in the kernel mode, it will complete its execution and only when it is moving back to the user mode, the process can be preempted. The process cannot be preempted in kernel mode. But in later versions of Linux, the kernel was made fully preemptive. So, if the kernel is made fully preemptive, say if a high priority process arrives and some data structure is being modified in the meantime in the kernel mode, what will happen to the data structure? How do we ensure that the integrity of data is taken care of? So, for that you need to have some mechanisms. There are some mechanisms that are being included in the Linux kernel. So, the task can be preempted now when it is running in the kernel. So, how is this taken care of? The first technique is, the one thing is the Linux makes use of two techniques for protecting critical sections. One is Linux provides spin locks and semaphores for locking in the kernel. So, if there is a very important data structure the Linux is going to use, the operating system is going to use, then the data structure is locked before accessing. So, even if the kernel is preempted, no other task can modify this data structure unless this first process which locked that unlocks it. So, you have two techniques as I told you, one is the spin lock and the other is the semaphores. So, spin locks are generally used in symmetric multiprocessing machines. When you have multiple processors, then you can use spin locks, because spin locks waste resources. If you have a single processor and if you are using spin locks, then unnecessarily you will be wasting CPU time. So, when you have SMP machines, then you have multiprocessing machines, when you have multiple cores, then you can make use of spin locks. When you have single processor machines, the spin locks may not be helpful. In that case, you have two calls, kernel defined calls, which are used for enabling kernel preemption and disabling kernel preemption. So, before using the data structure, you have to disable preemption, and then after completing the usage of the data structure, you can enable the preemption. So, in addition, say if the kernel is not preemptible if a kernel mode task is holding a spin lock. So, how do you take care of this or safety of critical sections? You need to use spin locks along with enabling and disabling of kernel preemption, and this is generally done only when the lock is held for very short durations. If the lock has to be held for very long durations, then continuously using a spin lock will waste resources, and in that case you can use semaphores. So, if the lock is to be held for longer durations, then semaphores are used. And the second technique is that is being handled when you have interrupt service routines. So, if you have critical sections that are a part of interrupt service routines, then how is it taken care of? So, for this the processes interrupt control hardware is made use of, and by disabling interrupts during a critical section, the kernel can avoid the risk of concurrent access to shared data structures. So, when a critical section is being executed, interrupts have to be disabled. But what will happen if interrupts are disabled? If you are disabling interrupts for a long time, then all I/O will be suspended, all devices will wait until interrupts are enabled, the performance will degrade. So, you can't just like that disable interrupts when some critical section of code is being executed, because interrupt enable and disable are not cheap. So, what can be done? There is another mechanism that is being followed here. This kernel, this Linux implements an architecture by separating the interrupt service routine into two sections. So, each interrupt service routine will be divided into two parts, one is called the top half and the other is called the bottom half. And the top half is a standard interrupt service routine. So, whenever an interrupt arrives, an interrupt service routine will be executed. That interrupt service routine is nothing but this top half of the interrupt service routine. And when this top half runs, then the recursive interrupts will be disabled. That is, interrupts of the same number will be disabled, but other interrupts can run. So, whatever is important will be first executed during this top half. Suppose if their packet has arrived in the network and if the network interface card is interrupting, then packets will be collected from that buffer and put into the kernel's buffer, and later it will call the lower bottom half of the second half of the interrupt service routine. So, the bottom half of the interrupt service routine is run after this top half completes execution. So, during the execution of the top half, the interrupts will be disabled, but when you are executing the bottom half, interrupts will be enabled. That is, we ensure that for a long duration of time, the interrupts are not kept disabled. So, bottom half of a service routine is run with all the interrupts enabled, and there is another small miniature scheduler which will ensure that the bottom halves will never interrupt themselves. So, the bottom half scheduler, as I told you, is invoked automatically whenever an interrupt service routine exits. So, whenever an interrupt service routine exits, then there will be a number of bottom half routines that are waiting, and the bottom half scheduler will choose one among these bottom half routines to execute. Suppose when a bottom half is executing, if another interrupt occurs, then that interrupt can request that the same bottom half will execute, but the execution will defer until the one that is currently executing or the currently running completes. Suppose the bottom half is executing, and if another top half routine has to be executed, then that is allowed. So, execution of the bottom half can be interrupted by a top half, but it cannot be interrupted by another bottom half. So, here we can see that even in each interrupt service routine is divided into two parts, the top half and the bottom half, top half getting higher priority compared to the bottom half. So, this top half bottom half architecture is completed by a mechanism for disabling selected bottom halves while executing normal foreground kernel code. So, normal foreground kernel code is given higher priority compared to bottom half routines, and interrupt handlers can code their critical sections as bottom halves. The important work can be done with the top half, and the critical sections can be coded in the bottom half. Now, when the foreground wants to enter a critical section, it can disable, as I told you, foreground gets higher priority compared to the bottom halves. So, it can disable any relevant bottom halves, so that any other critical sections cannot interrupt it, or it can prevent other critical sections from interrupting it. And at the end of the critical section, the kernel can re-enable the bottom half, and it can run any bottom half that have been queued up by top half interrupt service routines during the critical section. So, just look at this, this shows the priority. You have top half interrupt handlers having the higher priority, and then you have bottom half interrupt handlers, and then you have kernel system service routines, and then you have user mode programs. So, each level can be interrupted by code which is running at a higher level, but it will not be interrupted by code running at the same or a lower level. So, summary, we have learnt in this module how user process scheduling is taken care of in Linux using this completely fair scheduler. Then we learnt how real time process scheduling is handled in Linux, and we also saw how kernel task scheduling is handled in Linux. References, thank you.